Welcome to the last lecture in the linear regression series for the LACOL data science summer class. I'm Professor Miller again, and what I want to talk about now is some of the implementation issues in the GermanTank problem. So in the last lecture, we talked about the theory behind it. In the lecture before that, we talked about why it was such an important problem. What I want to do now is talk about how you can try to use linear regression, which is, after all, the theme of this week, to solve this problem, or at least sniff out what the answer should be. Now, there will be some interesting implementation issues. So let's review what regression is. So we believe that there's some linear relationship yi equals axi plus b, so y equals ax plus b. We talked about how there's three different metrics we could use. You could look at just the difference, the sign difference, but that's bad because a positive error can cancel negative error. You could look at the absolute value of the difference for your error, but then calculus is not available. Or you could use the sum of the squares of the errors. And now calculus is available. But unfortunately, we saw that there were some issues in that sometimes you got the slope, but wasn't so good on the constant. All right, so here was the formulas we had at the end of the day. And here's what happened in our first attempt to apply it. So we see that this does not look like a linear relationship. Now, a lot of it is a function of what are you plotting. So here I made the choice to plot n minus m as a function of m over k. So what we're doing is we're choosing a value of big N, we're choosing a value of k, and we're randomly choosing sets of size k from the points 1 through n. So if k equals 8, we're randomly choosing 8 points from 1 to n. If k equals 12, we're randomly choosing 12 points from 1 to n. And every subset of size 8 or every subset of size 12 is equally likely. And we know that the number of tanks produced has to be at least as large as the largest number observed. So why don't we just plot n minus m, how much we need to add to our guess, as a function of m over k? Because it seems reasonable from our theory talk before that it should depend on the ratio of m over k. As n goes up, our guess should go up. As k goes up, we've observed more tanks, we should have to inflate by less. And so if we try to plot it like this, we get a terrible fit. And one of the reasons is that we have m on both sides of the equation. So we really can't view it this way. If we use logarithms, we can plot the log of n against the log of m and 1 over k. Remember, we have the factor the log of 1 plus 1 over k. If k is large, the log of 1 plus 1 over k is approximately 1 over k. And we get what looks like a really good plane. And this is the generalization of the best fit line, the best fit plane. The data goes very nice there. But this is a little bit hard visually to see and understand what this is. So a whole industry exists on how to present data in a clear, meaningful way. So let's go back. We know n, according to theory, is supposed to be 1 plus 1 over k times m minus 1. Let's pretend we don't know that. And let's fix a couple of values of k, choose a bunch of values of n, and for each one of those, we'll observe a value of m, and then try to figure out what is the best fit line of the form, number of tanks is some number a times the maximum observed times our m plus b. So we're fixing k. So really this slope constant a depends on k. And this number b might also depend on k. And we want to see how the number of tanks varies as a function of the maximum observed serial number for a fixed number of tanks. So we're doing k equals 1. So the theory predicts n should be 2m minus 1. And the best fit value we get is this strange absurdity of n is 0.784m plus 2875, 2,875. We know that this formula can't hold forever. So you have to be careful about extrapolating formulas in large regimes. This is the best fit line you can get in this region using this method. But if you let n get very, very, very large, then your best fit eventually, n is going to be less than m. And you should not be predicting fewer tanks than you observe. As an example where this can be seen is think about special relativity. So imagine you are on a train and the train is moving at 60 miles an hour, and on the train you're running in the same direction as the train as 5 miles an hour. So someone on the ground will look at you and see that you look like you're moving at approximately 65 miles per hour. And you might think speed is additive. If the train is going 100 and I'm going 5, then I'm really, as if the train is going 60, I'm going 5, then I'm really going 65. It turns out speed is not additive. It's only approximately additive if the speeds are small. But as you get closer and closer and closer to the speed of light, there's a very complicated formula, and nothing, according to current theory, can go faster than the speed of light. You won't see that small correction for small values, but you will for large values. So if you try to extrapolate to objects going close to the speed of light from objects that are going a very small amount of the speed of light, you will get the wrong formula. So we need to be very careful. But when we see this 0.784, we should be suspicious about how good the fit can be, because that should not be less than 1. Now looking at k equals 2, again we have an issue. The best fit line should be n is 1.5 m minus 1. We've got 0.964. It's still less than 1. So there are some issues. It's an interesting question as to how these dots are distributed. I'm choosing different values of n. Why do we have more things here than there? Well, this is being spread out over a shorter region. This is now looking at k equals 5. The best fit value is 1.2 m minus 1. Well, now at least our best fit line is greater than 1. It's 1.037. So maybe as k gets larger and larger, it's going to be a good fit again. That maybe this is an effect of small values of k. I shouldn't be trying to apply this statistical analysis for small values of k, although we might want to. So here is trying to do it another way. Let's look at m now as a function of k and n. So we'll say the maximum observed should be c times the number of tanks plus some constant d, where c and d can depend on k. This actually does a much better job. Theory is m should be 0.5n plus 0.5, and our best fit is 0.496 plus 10.5. So, continuing the theme we've seen, the method of least squares does a much better job getting the slope than getting the intercept. This plot looks much better than the previous plots. If you go back to k equals 1 over here, it seems to be doing a little bit better in terms of the fit. But it's still not great. This is off by a bit, but it's not horrible. We could try k equals 2. And again, we're getting a great job with the slope. The slope's almost perfect. But we're having some issues with the constant term. K equals 5. Again, issues with the constant term, but a pretty good job with the slope. Here's one way to fix things. So we go back to our formula, n is equal to 1 plus 1 over kn minus 1. And what we're going to do is we choose a value of n, and we're going to do 100 different runs for each value of n. And then we're going to take the average maximum observed for each one of those, and we're going to plot that. So this is going to squish our graph a lot, because we're going to use the average values. And now, theory is 1.5 m minus 1. We get 1.496 m plus 171.2. So again, as always, we're not doing a great job on the constant term, but we're doing phenomenal on the slope. By doing this level of averaging, we're in great shape. I'll say one last thing about this. We could do this, of course, for k equals 2 and 5 and all that. You'll see similar results. But what's wonderful about this is we don't need to know how to derive the theory here. We can do some simulation. And by doing the simulation, we can predict what the answer should be. Now, this is the prediction for a fixed value of k. This is the value k equals 1. We can do this again for k equals 2, 3, 4, 5, etc. But what's nice is if we were trying to figure out what our formula should be, we can now use statistics to guide us to that. And to me, this is one of the most powerful applications of linear regression, is sniffing out what this relationship should be. So the question is, can we actually use linear regression to somehow suggest that the slope should be 1 plus 1 over k? Well, let's plot the best fit value of the slope as a function of the number of observations. So we keep changing the value of k. So down here, this should be k, not number observed. This should be k. We have different values of k, and we have the best fit values of the slopes. of 1 plus 1 over k. Not surprisingly, as k gets very, very large, the slope is getting very close to 1. If you observe more and more tanks, you should have to inflate by less and less. So this number observed should be a k over here, and this is the plot. Well, when you look at a plot like this, it's hard to really see what that relationship is. So by now, you should be used to doing log transforms. So if we plot the log of both, so it's a log-log plot of the best fit slope versus the value of k, and you can see this incredibly beautiful relationship. And so when we do a plot, well, we can look at the log of a minus 1, instead of just the log of a. And the reason is, if you look at the plot, we know everything seems to be converging to 1. Why not throw away that thing that we seem to know? So we look at the log of a minus 1 versus the log of k. We get the best fit line is negative 0.999 log k minus 0.007, which is suggesting, if you do a little bit of algebra, the relationship 1 plus 1 over k. So if we take a as 1 plus 1 over k, if we subtract 1, we get 1 over k. If we take the log of 1 over k, we get negative log k. Notice we have almost exactly negative log k. It's negative 0.999 log k plus a small little constant. But by doing this analysis, we're able to sniff out how the constant in n equals am plus b depends on k. So this is a tremendous power. We can actually experimentally find this formula. Now we'll be a little bit off by the minus 1, but that's fine. The minus 1 isn't so important. The more important part is how it depends on the number of tanks observed and the largest one seen. So I'll again just end by putting up the references. If you have any questions, always happy to chat. Have a great rest of the day.